Learning outcomes 1 and 2. Okay, and what we're going to do is produce a table for each of the types of radiation. For each we want to know what particle we're talking about, its charge, its mass, but what we're calling, remember, relative mass. So not necessarily how it compares. Similarly for speed, we just want relative speed, so not an actual value, but just how it compares to other similar things. What it consists of, and then 2 more that I'm going to add on based on the experiment we did yesterday. Range in the air, and so that's telling us how much air it would take to stop it. Absorbed by, okay, so what kind of material we could put in the way that could stop it as well. Okay, so our first particle is the alpha particle. This is not going to look that neat at the end of the day, I don't think, but right, it has a charge of +2. In relative terms, it's heavy. If you compared it to you or I, it's not. But compared to other subatomic particles, as we call them, it's heavy. Compared to you or I, it's slow. It would be very fast, but compared to other subatomic particles, it's slow moving. It consists of 2 protons. I'm going to have to come back to the and 2 neutrons and put it in. I'll put it in another line. It doesn't do tabs here, unfortunately. This is going to be annoying. What happened there? Right, I don't know what's happened. I just think I need to put it in there then. 2 protons. And 2 neutrons, and I just need to move my headings along a bit. So can anyone remember roughly what range in air we got yesterday for the alpha particles? Yeah, a few centimetres kind of. It's often, and it's not a kind of hard and fast rule that they will only go a certain distance, but it's usually somewhere in the range 2 to 5 centimetres. And what could we use to stop it? Yeah, a sheet of paper. It was actually cardboard, but okay, it is often written just as a sheet of paper. Okay. Our beta particle, our research told us it has a charge of -1. All right, it's about 1/8000th the mass of an alpha particle, so it's much lighter. But it doesn't belong in the nucleus, so when it's created from this neutron decaying into a proton and an electron, it's fired out at a high speed. It consists of 1 electron, Range in air, anyone remember roughly for that one yesterday?
50 centimetres.
Yeah, it's usually around about, but you'll quite often see it written anywhere really between kind of 20 to 100 centimetres. I'll put it as kind of 20 to 80 centimetres, but that sort of order of magnitude would say. And what absorber could we use to stop it? It was, yeah. It was a few millimetres of aluminium. So even that thin, have you ever seen foil used in the kitchen for baking and stuff like that? That's usually aluminium. That wouldn't be thick enough to stop. You really need a few millimetres worth to stop the beta particles completely. And then lastly, gamma. Well, at first it appears a bit boring. Right? No charge. No mass. It is, though, very fast, i.e. speed of light. Right? Oops, that didn't work. 3. Three times 10 to the power 8. Oops, I better put in my units. Meters per second. And it consists of various different ways of doing it. I've abbreviated here just to save a bit of space. See it as an EM wave, or sometimes written just as this idea of its pure energy. Because that's what an EM wave is. It's got no mass, it transfers energy, so it's just carrying pure energy. Now I've used abbreviation there. If this was an exam, you'd have to write it out in full electromagnetic. Range in air. What did we discuss about it? It's effectively infinite. Okay, it doesn't really have a range in air. Air doesn't have a big effect on it in terms of absorbing it. So what did we have to do to absorb it? It was lead, okay. So a few centimetres of lead. Or, Liam, can you remember you suggested something else?
Rock.
Yeah, rock. So if you were designing a building, you would need a few metres of concrete stroke rock to stop it.